Hi, everyone. My name is Yuval Gitlitz, and I'm a PhD student at Ben-Gurion University, Israel. And I'm here to present you our paper, Improved Weighted Additive Spanners. This paper was written by me, together with Michael Elkin and Ofer Neyman, and we are all from Ben-Gurion University. So let's get started. We'll begin with a few definitions. Let G be a weighted graph on n vertices. I will also call it sometimes during this lecture the original graph. And now we denote by dg/uv the distance between two vertices uv in the graph G. We say that a graph H is a plus beta spanner of G if it is, first of all, a subgraph of G, which means it has the same vertex set and subset of the edges of G. Additionally, for every pair of vertices UV, the distances in our spanner H is at most the distance between UV in the original graph plus beta. This is the reason it is called plus beta. For example, on the left, there is a very simple graph. And if we remove the edge BC, we get a +3 spanner. The distance between B and A and also A and C remains the same, while the distance between B and C increased by 3, from 2 to 5 by taking the paths B, A, C. Another type of spanner that we will consider during this lecture is subset-wise spanner, where we are also given an additional set of vertices S, and the distances in the spanner must not exceed plus beta only for pairs of vertices from S. If U or V are not in S, the distance might be unbounded in S. In this lecture, we will focus on the trade-off between beta and the size of the spanner, that is the number of edges, between order to n squared to order n. And the reason for that is because small size spanners for weighted graphs have seen some applications in distributed computing. The idea is that some algorithms and data structures depends on the number of edges in the graph. So running them on a spanner can give us an improved result. For example, you can look at asynchronous protocol design and compact routing tables. As you might have suspected right now, since our setting is weighted, beta must depend on the weights. For example, if we scale each edge by 100 from the previous graph, we get that by removing BC, we will get a plus 300 spanners. To tackle this, in weighted graph, we distinguish between two types of additive spanners. The first one is the more intuitive one, which is denoted by plus C W max, where W max is the weight of the heaviest edge in the whole graph, and C is usually some constant. If you look at our last example where we remove the edge BC, it creates a +1 W max spanner. Doesn't matter which scaling we are looking at. The second type of spanner is a bit more confusing, but more powerful and more desired, and it is denoted by +CW. Here, WUV is the heaviest edge, not in the whole graph, but in the shortest path between UV and G. So a +CW means that for every pair of vertices, the distance in the spanner is at most the distance in the original graph, plus CWUV. Again, if you forgot, WV is the heaviest edge in the shortest path between U and V, and not the heaviest edge in the whole graph. We will now look at an example to see why is it more powerful. Here we have a graph, and we are given two spanners. The first one removes the edge CB, and the second one removes the edge AB. The first one is +1 W max spanner. And as you can see, the distance between C and B was 1. Now it is 101, which is not a very good approximation. The second one is +1 W spanner, which gives a better approximation. Here, for example, the distance between C and A was 2, and now it is only 3. Because we are only allowing the additive term to depend on the heaviest edge on the shortest path, which is 1 in this case, the distances are in proportion to the shortest path. And we don't make them big unbounded. I hope this example made things a bit more clear. And we will now go through some prior work. In the following table, you can see a comparison between the prior state-of-the-art additive spanners for weighted graphs and unweighted graphs with the same size. And as you can see, the +2 and +4 have a matching construction for weighted graph with +2W and +4W, exactly like we want. The +6 spanner is a different story, as the only construction with the same size is +8 W max, which both use the inferior W max beta and is +8 and not +6, as we would want. For linear size spanners of size order of n, there was no construction before our paper available for weighted graphs. And for the subset-wise spanners, for the same size, the +2 spanner for unweighted graph is also an unmatched weighted spanner with beta equals to 4W max, which is again using W max instead of W, and is +4 instead of +2. We now look at our results. First, we give a construction for a spanner of size n to the power of 4/3 with beta equals to 6 plus epsilon W, where epsilon is an arbitrary small constant. You can think of it of 0.00001. Essentially matching the unweighted case up to an epsilon factor. We also give the first linear size spanner for weighted graphs with beta equals to O tilde square root of n W. This construction still leaves a small gap between the weighted and unweighted cases, so there is still room for improvement. Our last construction is a subset-wise spanner, which for the same size has beta equals to 2 plus epsilon W. Again, matching the unweighted equivalent up to an epsilon factor. Additional nice feature of our construction is that they are all using a very simple construction algorithm with only minor tweaks, though the analysis is a bit different between the construction. Now that we went through our constructions and our achievements, we want to sketch the proof of the +6 epsilon W spanner of size n to the power of 4/3. And for that, we will first define additional notation. And we denote by PUV the shortest path between UV and G. And our constructing algorithm works as follows. First, we initialize H as a subgraph without any edges. Next, for each vertex V, we add to H the lightest n to the power of 3rds edges connected to it. If V has less than n to the power of 3rds neighbors, we can add all the edges. The last step is where we assure our beta. We scan each UV sorted by WV, which again is the heaviest edge on the shortest path between them. And then we sort them by their distance in the original graph. If the distance between UV in the spanner is greater than the distance in the original graph plus beta, +6 plus epsilon WUV, we simply add the original shortest path, all the edges, to our spanner. And because of our last step, it is trivially, this is the whole algorithm by now. And because of step 3, we trivially get a +6 plus epsilon W spanner. If not, we would add the shortest paths between the vertices that are not plus beta. And now we will bound the size, which is where the fun part begins. Step 2 is also very simple. In step 2, we add at most n to the power of thirds edges for each vertex. There are n vertices, so n times n to the power of thirds equal to n to the power of 4 thirds overall. And step 3 is a bit more complicated and require more analysis. And for that, let UV be 2 vertices, for which the shortest path between them was added to H, and take any vertex X in the middle of PUV, in the middle of the shortest path. Now let A, B, and C be neighbors of U, X, and V respectively, connected with an edge weights at most WV, similar to what you see in the diagram. We will now prove our first lemma. Forgive me, I need to drink water. Okay. Specifically, we'll show that after adding PUV, again, we assume that PUV was added to the graph, the distance between A and B in the spanner is less than or equal to the original distance plus 4 WUV. And we do it by applying the triangle inequality twice, colored in red in our diagrams. First, we bound the distance between U and X using the path UABX. So the distance between UX is at most DGAB plus 2 WUV. And then in the second diagram, we bound AB by the path AUXB. And if we take them together, we get that the first lemma holds. The next lemma shows that by adding PUV, the distance of AB or BC in our spanner was reduced by at least epsilon over 2 WUV. And the proof here is by contradiction. After adding PUV, we can bound the distance of BC by the triangle inequality using the path CVX, B, and G, which equals to DGVX plus 2 WUV. Now, if the lemma is false, then before adding PUV, the distance between BC must be at most DGVX plus 2 WUV plus 2 epsilon over 2 WUV. This is exactly what the lemma claims. Now, bounding AB is symmetric, and we can get these two bounds, as you can see in the diagram. But now, if we look at the distance between U and V before adding PUV, and we can use the paths that go through VC, BAU. And we can see it is at most plus 6 plus epsilon WUV, the original distance. So PUV was not added by our algorithm, which is a contradiction, as we assume that UV are pair of vertices for which the path PUV was added. And we can see that the second lemma also holds. Now we are almost ready to put everything together. We say a pair of vertices A and B is set off when it is the first time the distance is less than plus 4 WUV, the original distance, which we can get using the first lemma. We also say that it is improved if its distance is reduced by epsilon over 2 WUV when adding PUV, which we can get using the second lemma. And now the important observation is that once a pair is set off, it can be improved at most order of 1/epsilon times. As you remember that we sorted the pairs that we considered to add in the paths by WUV. So any further improvement will be at least epsilon over 2 WUV, if not more. Now the last part of the proof is omitted in the presentation, where we show that if a path was missing L edges, there are omega of L times n to the power of 2/3 improved and set up pairs. You can find the details in the full paper if you are interested. Now, there are order of n squared different vertex pairs in the graph. So if we set omega of L times n to the power of 2/3 equal to order of n squared, we get that the last step adds at most order of n to the power of 4/3 edges, which completes our proof. And it's not only completing our proof, it also completes my lecture. So thank you very much for joining me. And bye, I guess.